Hi class, so now you've had some practice working on optimization problems. So now we're going to get into optimization problems in economics and science. So most of these will have to do with profit and cost. But you can see our learning goals. We have real world applications. We're going to be using the same algorithm. It's just that the type of question you're being asked will be slightly different. So let's just remind ourselves of the definitions of profit, cost, and revenue. Remember, profit is the amount of money you get to keep. Okay, it's what you take in, so your revenue minus your costs. Your costs, don't forget to consider any fixed costs you have, and then it's the cost per unit times the number of units you are making or you're selling. And then the revenue is the price per unit, so what you're selling the unit for, times the number of units sold. Okay, so when we're coming up with our restrictions, we have to think about some practical constraints as well as mathematical constraints, and those should be given to you in the question. Okay, so here we go again with a grade 10 level quadratics question, which could be solved with quadratic techniques, but we will solve with calculus today. So a commuter train carries 2,000 passengers, and right now it's $7 a person. But if you increase the price of the ticket by 10 cents, 40 less people will take the train. But similarly, if you decrease the cost by 10 cents, 40 more people will take the train. Okay, so what's new kind of is this next part is that it gives you the capacity of the train. So it gives you restrictions. So you can't have more than 2,600 people on the train. And fewer than 1,600 means that it's just too expensive. So we know that the number of passengers has to be between 16 and 2,600. So we will consider that in our restrictions shortly. So first of all, let's remember to think about how you're making money here. Notice it said to maximize revenue. So we are maximizing how much money we are taking in. So in this case, our revenue is going to be the number of passengers we have times the cost per passenger or cost per person. Okay, so both of these is changing with respect to how much we increase the price. So we want to have a common variable here, which is going to be the number of times we increase the price by 10 cents. So we'll say let X represent the number of 10-cent increases. Okay, so that is the simplest way to do it, the number of 10-cent increases. So if X equals 1, that means our cost is $7.10, not $8, be careful. And that our passengers would be 2,000 minus 40. Okay, so 1960 passengers. Okay, so now let's represent each of these in terms of X. So our revenue with respect to how many times we're changing the price. So the number of passengers is currently 2,000. But what happens every time that we have an X, this is reduced by 40. So we have to subtract 40 for every X. So 40X. And then our cost right now is $7, but it's going to increase by 10 cents every time we have an increase. Okay, so now we need to come up with the restrictions on the variable. So the restrictions have to be on the variable that we chose. So the variable X represents the number of price increases. So we need to figure out how does the number of passengers restrict how many price increases we can have. So this 2,000 minus 40X is the number of passengers. So if we set it equal to our max and our min number of passengers, we will find our restrictions for X. So for example, 2,000 minus 40X equals 2,600. Solving this equation will tell us the number of price changes that give us 2,600 passengers. And if you solve this, you get negative 15. Okay, it makes sense that it's negative because our number of passengers went up, so that means we must have been decreasing the price, so a negative increase. All right, and now we got to test our minimum. So 2,000 minus 40X equals 1,600. Okay, so when you solve this, you get 10. So with 10 price increases, so that's increasing by a full dollar, that means that we'll only have 1,600 passengers, so that's the most that we can increase it by. So now we have our restrictions. So let's rewrite. Well, you don't have to rewrite the function. You can just put the restrictions now, or if you had room, you can put a comma and put it next to the function here. But x has to be between -15 and 10. Okay, so now we go through our algorithm. We find the derivative of our function. Okay, so to find the derivative of this function, either you can use the product rule or you can expand and use the polynomial derivative. So I'm actually going to go back up and expand this into standard form because it's just easier for me to take the derivative that way. So if I go back and put the function in standard form, it's minus 4x squared minus 80x plus 14,000. Okay, so that's my current revenue function. There's my restriction. So notice this means that if there's no price changes, I'm making $14,000. So I'm looking to make more than that. So now my derivative is minus 8x minus 80. Okay, and so now I'm going to set the derivative equal to 0. And when you do that, you get x equals -10. So notice since I am putting the line that I'm setting equal to 0, if I can do that in my head to get to -10, then that's enough. You don't actually have to show this being set to 0, but you do need to include a line indicating how you got your answer. So therefore, that means there should be 10 price decreases, which means that the price should be decreased by $1, since 10 times 10 cents is $1. So it says, so now I'm going to make sure I actually answer the question, because you can ask a lot of different questions here. What is the revenue? How many price changes? But this says find the price to maximize revenue. So therefore, the price to maximize revenue is $6. Okay, so if you didn't notice about the $6 right away, you could just put this -10 back into your price function and you'll get $6. Okay, so now we're getting on to a cylindrical storage tank. So this will have to do with volume and the cost of creating it. So it's the cylindrical storage tank with a capacity of 1,000 cubic meters. And they want to build it in a warehouse that's 12 by 15 with a height of 11. So then it talks about the costs, which we won't actually need till the second page. So is it possible to build this container? So what that's asking is, does this warehouse have enough space to fit a cylinder that can fit that much capacity? So let's test the biggest possible container and just make sure that its volume is above 1,000. So the biggest would be a radius of 6, since our base is 12 by 15. The largest radius possible is 6, and then the height of the cylinder would be 11. Okay, and so the volume, remember, of any prism is the area of its base times its height. So in this case, the area of the circle, pi r squared, times the height. Okay, so we put pi and then 6 squared times 11, and we get approximately 1244 cubic meters. Okay, it doesn't matter exact here because we're just seeing if it's big enough to fit this 1,000. And so yes, that's much bigger than 1,000. So therefore, yes, there's enough room in the warehouse. Okay, yay. So now we have to figure out what our restriction is on the radius. Okay, so we already know that the high end of the radius, okay? The high end of the radius is 6. So we know that the radius has to be less than or equal to 6. But what is the smallest radius we can possibly have and still meet our requirement of 1,000 cubic meters? So that's what we want to say now. What is smallest radius. So volume is 1,000 and it fits in the space. That's our question. So we're going to create the smallest, the cylinder with 1,000 cubic meters that has the smallest possible radius. So that means that the height, the radius will be at a minimum when a height is at the maximum, right? It would be tall and skinny. So we know our max height is 11, so that's what we're going to force the height to be. Max height is 11, so that's what we're going to use. So we're going to take our volume formula, volume equals pi r squared h, and put in 1,000 for our volume, pi r squared, and 11 for our height. And when we solve this equation, we will find the radius that occurs when we have the volume and the highest height, which is the smallest possible radius in this case. So when you find this, you get your radius to be 5.38 meters. Okay, so therefore our radius has to be between 5.38 meters and 6. Okay. So now we want to solve the big question. We want to minimize the cost of the steel. Okay, we want to construct this with as little cost as possible. So here now this cost stuff is important. So all of these have a different cost. The base is made of a sheet steel costing 100 meter per square meter. The top will be 50 and the wall materials cost 80. So the total cost will be the sum of these. So let's break them individually out first and then add them together. Okay, so the cost of the base. So the base is a circle. So it's 100 times the area of the base, so pi r squared, right? And then the cost of the top will be 100 times the area, 50 times the area of the top, so 50 pi r squared. I don't actually need those brackets. And then the cost of the sides will be 80 times, so the area of the side is 2 pi r h. If you remember a cylinder, when you take the net out, that it becomes a rectangle where this is the height of the cylinder and this is the circumference of the circle because it's been unwrapped. So that's 2 pi r. So that's why you get 2 pi r times h. So notice that we almost have a function in one variable. Remember, to do any of this work, we just need a function in only one variable. The problem right now is this h. These are both in terms of r. We have an r here, but how do we turn this h into something with respect to r? Well, we know that the volume has to equal 1,000. So we can just rewrite our volume formula, pi r squared h equals 1,000. Because we know this number, we can rearrange this formula for h, and then it will be in terms of r. So h is equal to 1,000 divided by pi r squared. So now in our function, instead of the h, we can write 1,000 over pi r squared, and then everything will be in terms of r. So that's exciting. Okay, so let's go ahead and make our function then. So we're going to identify our variables. Let CR represent cost in dollars at radius r in meters. Okay, so we're going to do the sum here. So C at r equals 100 pi r squared plus 50 pi r squared plus 80 times 2 pi r 1,000 over pi r squared. Okay, so let's simplify this so we can collect like terms here. So 150 pi r squared. Okay, 80 times 2 times 1,000 is 160,000. And then notice here, this pi and this pi cross off, and we can also cross off one of the r's. So this is all left to be just over r. Okay, and then we write our restriction of 5.38 to 6. Okay, so this is our cost function, and now we're just going to go through our algorithm. So we find our derivative. So we get 300 pi r. And then in this case, you can either use the quotient rule, or you can think about this as r to the -1 and use that rule. But either way, you get negative 160,000 over r squared as the derivative of that part. Okay, and now we're going to set c prime at r, equal to 0. So that essentially means that 300 pi r equals 160,000 over r squared, okay? Because if you set this equal to 0, move this over because it's negative, this is what you get. Okay, so now you need to cross multiply to get this r squared up here. So you end up with r cubed equals 160,000 divided by 300 pi, okay, which is approximately 5.54 meters. Phew, it's within our restrictions. That's good news. So now you test your costs at your there, and then at either endpoint to check that you're getting the absolute best cost. And when you do that, you'll see that the one that you found through calculus is the winner chicken dinner. So to minimize the cost of the steel, the radius should be equal to 5.554 meters, and you can use that to find the height as well. All right, so there you go. There's 2 long questions about optimization with profit, cost, and revenue. Thanks for watching, guys. Hope you learned lots.